The goal of this video is to show you how to do joint control. In particular, we look at position, velocity, and torque control. That file is in the description, but when you play it, you will see that the pendulum is swinging freely. In this video, we will first go ahead and set the control mode using the graphical user interface. We'll look at all these three modes. Once we do that, we'll move on to setting the mode using Python. First of all, let's see what the position of the joint is. So if you click on joint, you see it's set to 2 degrees. So 0 degrees is the vertically upright position. Let's set it to 180, so it's vertically downwards. If you click on joint again, and if you click on dynamic properties, you see that there are control modes. These are the following ones: free, force, velocity, and so on. So here we'll explore these three. So let's look at velocity control to start with. I always recommend that put a very high limit on the torque, so it is never torque bounded. The default target velocity is 90 degrees per second. So you can see that it is actually turning, that is, it's basically rotating by 90 degrees every second. You can, of course, change that by going here and changing the value for target velocity. Next, let's look at the position control mode. Set to position. Always set very high limits for the torque and maximum force and velocity. Let's set the angle to 90 degrees. And then go ahead and play. It is 90 degrees. So clearly you can set the angle to any value you want by using the GUI. Let's look at force control. Here you can only specify a force. So let's specify a very small force. Let's say 3 Newton meters. You can see that that force is trying to get the pendulum to go to a particular angle, but it doesn't work because gravity is overcoming the force. We can, of course, increase that force to, let's say, 10, and then run this. And you can see that it becomes unstable. The problem with using the GUI is that it's kind of limited in terms of what you can do. For example, if you want to apply a force which is proportional to the position, you can't do it with this particular GUI. Also, if you want to switch between different modes, then it's very difficult to do that dynamically as the simulation is running using the GUI. So what we'll do next is we'll explore how to do the same thing using Python code. For that, we access object in 32 param, which is a way of setting the different modes. So we can set it to those 3 modes I talked about. We can also, once the mode is set, we can actually do velocity, position, and torque control. This, by the way, has been switched. This should be velocity and this should be position. Okay, so let's look at these 3 modes using Python script. First thing we do is we go to stand and we add a script, non-threaded Python. Okay, here's the blank script. What we have to do here is we want to control the joint. So let's get the joint handle, and then use the joint handle to do for 2 other interesting things. So joint equals sim.get object. Okay, so joint is specified here, and I'm getting the handle using sim.get object, and I've given it a name joint. Once I get this, now I can use some of the commands to set the joint properties. So for that, I recommend that you open the API reference, go to joint, go to int 32, set object in 32 param. Okay, so the way this works is you can use object in 32. You need to give the handle. So in this case, it will be joint. We need to give the parameter ID and then the parameter. Now, the specific thing we're interested in doing here is we want to set this to velocity control. So we need to look at list of all possible parameters here. Here we're looking for joint. So the parameter of interest here is the dynamic control mode. So let's click on this. And in dynamic control modes, we see that there are these several modes. Okay, so what I need here is I need these values. We copy paste them in my code. Again, this is just for reference. I'll comment it out. I also need something else. I need the parameter ID, which is this. Okay, and then let's go back to the command. This is the command. Okay, so I'm going to put all this together in the following fashion. This will set the mode. The object here is joint. Okay. Now since this joint is defined in a different function, I would need to make this joint as a global variable so I can access it right here. The parameter ID here is this one. And the parameter I'm interested in is setting the velocity. Now, since I've set the velocity, now I can go ahead and control the joint. So for that, I use sim.set joint target velocity. I need to give the object handle joint, and then I need to give the velocity. So let's say we set it to 0.5. If everything works right, then it will actually move at a constant speed with at 0.5 radians per second. So let's play this. Okay, so you can see that it's not quite going there, it's stopping. And that's probably because of the force limit we've set. So what I mean by that is, if you click on joint and you go to properties, you see that the force here is limited. It's always increase it to a large value. If you go to velocity mode, it looks good. And then position, it's all set to high. Okay, so let's go back and play this. Okay, all looks good. Let's stop this. Let's explore the position control mode. So let's comment this out. I will copy this part of the code. I need to set this to position control. So I'll change this to position. Instead of setting the target velocity, I need to set target position. Let me set it to 90 degrees. So math.pi divided by 2. So everything looks right and it works fine. Then you should see that the pendulum will go from 180 degrees to 90 degrees, so horizontal. So there it went to horizontal immediately. Okay. Last, let's look at the third mode, which is setting the force. So here I need to change this to force. I need to specify the force. For that, I'll use target force. I will define the force as a separate variable. So force equals 10. See what happens. So you can see it goes unstable. Now, I said one of the advantages of Python code is to be able to write force as a function of some other variables. So let's do the following exercise. Let me just change the joint angle to, let's say, 10 degrees. Okay. And let this pendulum move. And you can, sorry, I need to turn off the force. So we turn off the force, then we go to joint and set this to free. Okay. Now when I run this, you can see that the pendulum is swaying from 10 degrees to minus 10 degrees, and you just keep doing that because there's no dissipation. It keeps oscillating. Let's say we want to dissipate the pendulum, that dissipate the energy. So a good way to dissipate is to add a force proportional to the negative velocity. So for that, what we'll do is we'll first set it to force control mode. We need the velocity, so let's call that theta dot. And to get that, I'll do sim dot get joint velocity. And I need to joint handle, so it will be joint. Once I have that, my force would be, let's say, minus 0.5 times theta dot. So this is a damping force. And now let's assign the force. Okay, so if everything worked fine, then you'll see that the pendulum will be dissipating its energy. There you are. It is dissipating its energy. Okay. If you change this to 0, there is no force, then it'll go back to its original mode where it is swinging freely. So I'll comment all this out. Okay. So this basically showed you how to set the different modes in Python and then do velocity, position, and torque control. Let's move to another concept called finite state machine. A finite state machine is useful if you want to create behaviors, more interesting behaviors than just a single thing. So for example, we had position, velocity, and force control previously, but what if we want to do velocity control for some time, then switch to position control after some other time based on certain criteria? The way to do this is to finite state machine. Finite state machines has a start state, then it transitions to a new state, and depending on some conditions, transitions, it will switch from one state to another state. You can read about a finite state machine by using this link. In our case, we will do the following exercise, and I'll refer to this slide again as I program the pendulum. We'll start the pendulum in the vertically downward position. We'll use velocity control to get it to speed up. Then when it reaches a certain angle, we'll split to position control. We'll hold on the position control for 3 seconds and then transition to damping mode, so it dissipates energy and comes down to the vertically downward direction, in which case we'll switch the velocity control again. And so it'll just keep cycling between these 3 modes. These states, I'm going to give them names: FSM velocity, FSM position, FSM damping. So I'm going to show you how to program this one step at a time. So we'll start with this and then move along these arrows. First thing, let's put this pendulum back to its vertically downward position. So this will be 180. We can also ensure that the joint is set to free. Okay. And then if you run this, nothing quite happens, right? Because I commented the code out. Okay. First things first, let me just create those states: FSM velocity, FSM position, FSM damping, and I'm going to give them numbers. Now you could use them 0, 1, 2 to denote them, but I think it's much better if you give them names like the ones I've given here. What we want to do is I want to start the FSM in the state velocity. So I create a new variable called FSM. This basically keeps track of which state the pendulum is in. So FSM equals FSM velocity. Okay. I'm going to create a global variable for that because I'll be using it in the actuation code, and I'll also have to define it here, FSM. Now, the way an FSM is coded is the following: all transitions will come here, and all control actions, like what you do in the particular state, will come below here. So first of all, here I'm interested in controlling the velocity, the control action. So for that, I will say if FSM equal to FSM velocity, so it's in this particular state, then do the following control action. I want it to basically do velocity control. So I'm going to copy paste this code. So it sets to velocity control at and moves it at 0.5. So let's see how this plays out. Okay, so nothing different here. It's just moving it with a certain speed. Okay, what we've achieved here is we've been able to get it to do velocity control. So basically, this bubble has been created. Now let's try to explore how do we set this transition. So when it is plus or minus 30 degrees or 0.5, we need the finite state machine to switch to FSM position. Okay, so that is a transition, and the transitions are all going to be here. So we say if FSM equal to FSM velocity, we also need the angle. So I'm going to get the angle theta, and that can be got by using sip.get joint position. This is for joint, and I'll say and theta is greater than minus 0.5, so that's minus 30 degrees, and theta is less than 0.5 or 30 degrees. Then I want it to switch. So FSM should be FSM position. And to confirm this, what I'll do is I'll say print transitioning to FSM position. So we've basically programmed this, and I'm going to check this in just a bit. But before that, let me just program this particular state machine or state controller, FSM position. So this code will look very similar to this code here, but it will be for position control. So let's take that. FSM position, you need to set the position control mode. That will be position. And then we want target position, and that, let's say it's going to be 0, 0 being the upward position. So if everything worked right, you'll see that it starts with velocity control mode, goes. Once it reaches 30 degrees, it should switch to position control, and then it just stays there. Okay, so you can see that also printed transitioning to FSM position here, indicating that it actually went through this if control. It only went through that once. Okay. Okay, now what we're going to do here next is we'll hold on to this position for 3 seconds. There's the FSM position, and then transition to FSM damping, where we'll damp out the oscillation. So let's program that. Okay, so that is done in a slightly different manner. I need to basically start counting time from the time it transitions to FSM position. So I'll create a new variable called t position, okay, which stores the time in FSM position. I'll initialize it to 0. It will be a global variable. I'll also tell the code that it's a global variable in this function actuation. Now what I need to do is when it is transition to FSM position, I need to set t position to whatever the time it is. So the time at this moment, but this has not been, this is a variable I need to define. So I'll call that, I'll create it here, sim.get simulation time. So this gives me the time continuously, but when this particular transition occurs, it basically stores the time at that moment in t position. Okay, now I want to say that and t minus t position is greater than let's say 3 seconds. Sorry, this is not the place. My bad. You need to program it here. If FSM equal to FSM position and t minus t position is greater than 3, then we want to transition to FSM damping. Okay, FSM damping being defined here. And we want to print transitioning to FSM damping. Okay, so once it has transitioned to FSM damping, we want it to basically apply the necessary control actions. So FSM damping. So we'll use what commands we developed here. Okay. Set to force control, get the velocity, apply a force, set it on the joint. Okay, so if everything worked right, we'll have it damping out. Now, let's try playing this and see what happens. You can see it went to FSM damping, but it's not really falling down. So what we'll do is, to make that happen quickly, I'm just going to change this position from being 0 to 0.1, so it'll fall immediately. So it's going to be 0.1 from the vertical. It's damping, and so now it's damping out. Okay, so going back, we've programmed FSM velocity, FSM position, FSM damping, and now the last transition, we want it to transition to FSM velocity. Now, when we want to do this is when the pendulum is in the downward position and the speed is close to 0. So let's see how this is programmed. So downward position and speed is close to 0. The speed close to 0 is straightforward. However, there is a problem with downward position. If you look at the joint, you see that position is minus 180. If you do minus 175, it's there. And then if you do plus 175, it's here. And so there is this thing which is, there's a discontinuity, the way the pendulum is modeled. It goes from 175, instead of going to 180, it actually switches to minus 180. So that discontinuity makes it difficult to specify the actual joint angle in the downward position. Instead of using that joint angle position, we'll actually trigger it using just the speed, and we'll use a time, just like we use the position time. So what I mean by that will be clear in just a moment. I'm going to create a new variable called the damping. This is to transition to velocity. We'll assign it to 0. Let's create a global variable, the damping. Okay, now what we want to do is, if FSM equal to FSM damping and theta dot, so I need theta dot, which has not been specified, but I do have it specified here. So why don't we just move it right here so it's accessible to the entire code? So we want to have theta dot should be greater than a small value, so maybe 0.1, and theta dot should be less than 0.1. So it ensures that theta dot is between minus 0.1 and plus 0.1. And we also need the time. So what I'm going to do is I'm going to create, store the time and damping took place. So when this transitions, you store the damping time, and then we say T minus T damping is greater than 4. Okay, so it waits for 4 seconds before it makes the transition. And we want to go to FSM equals FSM velocity. Okay, and we want to print transitioning to FSM velocity. Now, we do not need to program FSM velocity because that's already been done. Okay, so let's see how this works. Okay, there is an error. Okay, there's an invalid syntax. I accidentally put this column. Let's run this now. So velocity control, switch to position control, wait for some damp out oscillation, wait for some time. So you can see it's transitioning to FSM velocity, but it's not really going at uniform speed. The reason why it's doing that is because remember that in order to go to FSM velocity, it goes through FSM damping. But in FSM damping, we specify a minimum force. That force persists in the memory. So we need to clear that force. We want to make that a very high value, just like we did it with the GUI. Transition from FSM damping to FSM velocity, I'm going to set this value to a very high number. So that's never going to constrain the system. So now let's run it. Velocity control, position control, wait for some time, damping the oscillations out for 4 seconds. And now it goes back to velocity control mode. Position control, back to damping, and so on.